So the final section we're going to study in Chapter 9 on conic sections is about hyperbolas. So far we have reviewed circles, or we've studied circles, parabolas, and ellipses, and now our final one is the hyperbola. So it says, by making one small adjustment, to the definition of an ellipse, we create the conic section hyperbola. A hyperbola is the set of all points P in a plane such that the difference between the distances from that point P to two fixed points is a given constant. So that difference never changes. It is a constant. Now if you recall, in an ellipse, that was a sum. So we added those up and we got a constant sum, a constant number. Here we're going to take the difference between them and get a constant number or difference. So what do we call those two fixed points? Well, like an ellipse, like a parabola, that fixed point is singular, it's a focus. In an ellipse, it is double its foci, just as it is in a hyperbola. In an ellipse, if you recall, your foci are on the inside of the figure. In a hyperbola looks like this. It's kind of like two parabolas back to back going opposite directions. This time your foci are going to be out here, right? So I don't know if that's inside or outside, I guess, but it's kind of like the parabola where it's opening toward the foci. Okay? So we'll talk more about that as we go along. The center of the foci is the midpoint of the line segment joining its foci. So here I joined these foci, and the center is halfway in between. So the center is also halfway in between these vertices right here as well. So this would be my center. Okay, so let's kind of look at that definition. Remember, the definition was the difference between a point on the hyperbola and the two fixed points, or the foci. So I calculated the difference the distance between F1 and P. So this is the point on the hyperbola. This is focus number 1. This is focus number 2, and the distance between P and F2. And right now that distance is 4.44. Well, if I maintain that exact distance, right, this difference does not change. Oh, it did change. Now it's positive. So no matter what, when we go up here, these differences between the blue lines, right, so F1, why is it suddenly negative now, right? Because my distance between P and F1 is now the bigger number, and this is the smaller number, but I'm keeping this the same. So I'm always going to have a plus or minus sum over here. That's why we have two sides to our hyperbola. So, but what does it mean? It means this distance minus this distance will always be the same measure of negative 4.44 or positive 4.44. Okay, so notice this is the distance. If this is a straight line, I think I'm a little off, I missed it. From foci to foci, right, it's going to be the sum of these two things. It's going to be from foci to foci. So what is this number here then? That's the distance from vertex to vertex. Okay, we're going to come back and talk about that in a little bit. But here you can see from definition of hyperbola, it is the difference. It's a constant difference between the point on the hyperbola and to each focus. All right, so let's sketch it here. Make a sketch of the hyperbola as made. We will consider the vertical and horizontal hyperbolas only. So we are only, luckily, going to study vertical hyperbolas. They're going to open straight up, straight down, or horizontal hyperbolas opening right and left. So we're not going to rotate them and like open them in the second and fourth quadrants, like let's say. So we're not going to do something like this and rotate it. It's going to be straight on, up and down, and that's it. So let's make a hyperbola. What we'll do eventually when we graph is we'll make a rectangular figure, I like to do, and then we'll make asymptotes coming through. You couldn't see any of this on the Geometer Sketchpad, but what you could see is the center. So in this case, our center is always going to be the origin. It's going to be at 0, 0. And then if we wanted to make a vertical hyperbola, we would put our vertices on this rectangle and it's going to open toward these dotted lines, which are called asymptotes, right? So this is an asymptote right here. So remember, graphs don't cross asymptotes, they just approach it. So that's what it's going to approach as it continues on to infinity up here on the y-axis, and as x continues to get bigger. So this right here is a vertical hyperbola. If I wanted to make a horizontal hyperbola, I would put my vertices right here on the x-axis. Notice these are on the y-axis, and then I would open it up right and left. So this is now a horizontal hyperbola. So where would my foci be? Well, in a vertical hyperbola, your foci are going to be above or below those vertices, right? So these are going to be examples of where your foci might be. Obviously, I'm not necessarily being accurate right here. This is another for horizontal. It could be to the right or to the left. So not on this inside rectangle, but on the outside out here. So we have our center, we have our foci. The other things we need to identify are the A and the B. Remember the distance from the center out to the foci, that's a C. That's a length of C. Always, from the center to a foci, that's true in an ellipse, that's true in a hyperbola. Remember, what is C in a parabola? It's the distance from the vertex. The parabola doesn't have a center, so it's the distance from the vertex to the focus. Okay, so if we're going by definition, it says, again, it's a set of all points P in a plane such that the difference between the distances from point P to two fixed points, or to the foci, is a given constant. So if we name that constant to be 6, then you can do the distance formula and get an equation of a hyperbola. So what is point P? Well, point P we would call x comma y, right? So setting that up, we want to see that from the distance from x to negative 5, 0, right? So I'm doing the distance from here to here, plus the distance from x, y to positive 5, 0 will equal 6. Well, here it's the absolute value because we have it opening up and opening down, right? Remember how you saw that in the Geometry Sketchpad sample. So therefore, you can either put absolute value around this, or you can put it plus or minus 6. Now, obviously, we don't have enough space to do it with plus or minus. I'm just going to do one or the other. And actually, it's not going to matter in the end. We're still going to get an equation that looks like this. So what do we have to do? We have to move this thing over to the other side, right? By subtracting this square root, we get x minus 5 squared plus y squared. It disappears over here. Now we have to square both sides. So square both sides, and then you're going to continue. So go ahead and do that. And so continuing that process, you should have went through, move that over there, square both sides to get this. Things cancel. You isolate that one singular radical on its own. You once again square both sides to get this, and then you divide everything by 144, and you see that x squared divided by 9 minus y squared divided by 16 equals 1. So it looks very similar to the equation of an ellipse, except you have a minus sign in here instead of a plus sign. So if you didn't figure out that distance formula, you can follow mine here. I started going down this direction, popped up, continued in blue. Okay, so what does this mean graphically? So I'm going to go ahead and sketch it over here. So graphically, the first thing you do is you look whatever's underneath the x. So 9 is underneath the x, so you take the square root of 9 plus or minus the square root of 9. That's 3, so you go to the right 3, and you go to the left 3, and you put your points there. And then we look at our y, and we have plus or minus the square root of that number. So plus or minus the square root of 16, so we're going to go up 4, and we're going to go down 4. Once you do that, I would make a dotted rectangle going around. So you have exactly these 90-degree angles, so it makes a rectangle. Go all the way out to the corner, so your width is from -3 to 3, and your height is from -4 to 4. Okay, now because the x squared was first, this means we have a horizontal hyperbola, and here are my vertices. So before I can draw that though, we draw our asymptotes. Your asymptotes go through the center, and then these corner points are important. That's why it's important to go all the way out to the width and all the way up and down to the height. So we go through the center and through these corner points, make dotted lines, and those are your asymptotes. So now I can draw my hyperbola. It always touches the rectangle or the box right here. So it's the actual points are right here on the x-axis, and then you go out and you approach the asymptotes. So the blue part is the only part that's really the sketch of the hyperbola. Everything else is on there just to help me sketch the hyperbola, but it's not part of the actual graph of the hyperbola. So when it talks about intercepts, x or y intercepts, well here this only has x-intercepts, right? So when your positive term, so x is the positive term, so that means my x-intercept, I'm going to have x-intercepts and no y-intercepts. If my y squared came first, that means I would have y-intercepts and no x-intercepts. So in this case, I have two intercepts. They are 3, 0 and -3, 0. Okay, how about my domain and range? Well, if you notice, everything in here, right, so all this stuff in here is not part of the graph. And it continues getting wider and wider and wider. So that's not part of my graph. So this is exclusion from what? From my domain or from my range? Is that excluded from my domain or from my range? Well, hopefully you're saying to yourself, oh, it's excluded from the domain. Why? Because this graph goes infinitely up, forever and ever and ever, forever and ever up, forever and ever down, forever and ever down. But it only goes right here and left here, and all this is blank in the middle, which is my horizontal distance. So my domain is from -infinity until this point right here, which was -3. Does it include -3? Yes, it does. And then we also go from 3, and then we go continuously to the right. So it starts at 3, that's my lowest number, it goes to infinity. Remember, your infinities are exclusive, but it includes these values. What's another way of writing that? You could have written this. Same. But hopefully you're understanding the interval notation now. Finally, we need to identify our asymptotes. Well, your asymptotes are these equations of your lines right here. Can you get an equation of a line? I certainly hope so. This is easy. Remember, it's y equals mx plus b. We need to find the y-intercept and the slope. Well, hopefully you can see, what is the y-intercept of your asymptote? It's 0. Okay, awesome. So this disappears. So it's just y equals mx. Well, what's my slope? Okay, we go over here. What is your slope? It's rise over run. So what do? We went up 4. Remember, these are the points down here, up and down 4, and right and left 3, and right 3. So what is my slope? My slope is 4/3. That's only for one asymptote. What about this asymptote going up and to the left? Well, that's +4 over -3. So your asymptotes you can write as y plus or minus 4/3 x. So these numbers under here are what helped me get my asymptotes. Remember, asymptotes are equations of lines. It's what it's approaching, but it's never going to cross. So take a moment to digest all of this, then study maybe the table on the back of this page. So study this table at the top. Read through this on your own, and then we'll come back and talk about it. See what we just did, see if it makes sense, and then we'll come back and talk about it.